It's time for another chemistry review. This time it's 3.06, Ideal Gas Behavior, where you will learn about Dalton's law of partial pressure and Graham's law of effusion. I can hardly wait. Here we go. All right, so why exactly is it can you smell dog poop on the corner of your lawn sooner in the summer than in the winter after the dog takes a dump on your lawn? Now, I am not condoning this. Whoever walks the dog needs to carry a bag to clean up the poop in. But in the event of irresponsible dog poopage, you will definitely smell that poop quicker from your front door in the summer than you will in the winter. Now, why is this? Stay tuned and find out. All right, so first of all, let me introduce to you John Dalton, so-called father of modern chemistry. He actually was the person who discovered atomic mass. And it was atomic mass that allowed a periodic table to be developed. He actually made use of Avogadro's hypothesis that states that equal volumes will contain equal moles to expand upon that to the law of partial pressures, which states that if you have a mixture of gases and you want to get the pressure of that mixture of gases, the total pressure of that mixture of gases will equal the sum, which means you add them up, of the partial pressure of each gas in the mixture. So if we have a mixture of helium, neon, and argon with a total pressure of 6 atmospheres, our pressure of each individual gas will have to add up to that 6 atmospheres. 1 plus 2 plus 3 does in fact equal 6. I don't even need my calculator for that. I'm so proud. Anyway, Avogadro's hypothesis says that equal volumes at equal pressures and temperatures will contain equal number of molecules, which means that if you have twice as many molecules, you'll have twice as much pressure or twice as much volume, depending on which one you're holding constant. So again, it's making the assumption that all gases behave like ideal gases. And at STP, to temperatures 273, the pressure is 101.3, gases behave enough like ideal gases that we can apply these laws to it. So here we have a sample of hydrogen. 5 liters at 20 degrees Celsius, 5 liters at 20 degrees Celsius. We got 0.6 moles of hydrogen, 1.5 moles of helium. The pressure of the hydrogen is 2.9 atmospheres. The pressure of the helium is 7.2 atmospheres. You'll notice that there are more moles of gas and therefore a higher pressure for helium than there is for hydrogen. If we have more gas, that gas will exert more pressure, everything else being equal. Now, if we put these two gases together in the same 5-liter container at 20 degrees Celsius, and you want to get the total pressure of this mixture, you just simply add the partial pressure of each gas in the mixture to get the total number of moles and the total number of amount of pressure. Okay, so the pressure of one gas plus the pressure of the other gas in the mixture will add up to give you the total pressure of those mixed gases together. Okay, so here are some examples. 4? That's weird. A sealed container contains hydrogen gas with a partial pressure of 80 kilopascals and nitrogen gas with a partial pressure of 30 kilopascals. What is the total pressure in the container? Well, this is very easy. Actually, you just take the two pressures and you add them together. Now, what if one of these pressures was in atmospheres and the other in kilopascals? No problem. Just convert one to the other so that you have like units that you can add together. Number 2, a cylinder contains helium and argon. The total pressure is 5 atmospheres. The partial pressure of helium is 3.5 atmospheres. What's the partial pressure of the other gas? Well, they both have to add up to 5. And therefore, 3.5 plus what is 5? 1.5. So the pressure of the missing gas is 1.5 atmospheres. Number 3, a planet is discovered and it contains 30.0% carbon dioxide and 70% of methane by pressure and a total atmospheric pressure of 60.0 kilopascals. What is the partial pressure of each gas in this atmosphere? Well, since carbon dioxide makes up 30% of the pressure and methane takes up 70% of the pressure, just take 30% of the pressure to get carbon dioxide's partial pressure and 70% of that pressure to get methane's share of that pressure. Pretty easy. Number 4. A sample of a mixture of gases contains 2 moles of oxygen gas and 1 mole of nitrogen gas. If the total pressure of the sample is 300 kilopascals, what is the partial pressure of each gas? Well, we have 2 moles of one kind of gas and 1 mole of the other kind of gas. That gives us 3 moles total. And since the total pressure is 300 kilopascals, if we divide that by the 3 moles, each mole will exert 100 kilopascals. Since there's 2 moles of oxygen at 100 kilopascals each, oxygen's partial pressure is 200 kilopascals, and nitrogen, with only 1 mole at 100 kilopascals each, will be 100 kilopascals. And you'll see how the partial pressures, 100 and 200, add up to the total pressure of 300. Just a nice way to check it. Number 5. Oh, if you hear thumping and all kinds of crazy noises, it's my cat Percy tearing up my studio. Not to worry, I haven't lost much blood yet. Number 5, a sample of ammonia, NH3, is decomposed into its component elements of nitrogen and hydrogen. What is the partial pressure of the hydrogen if the partial pressure of the nitrogen is 6 atmospheres? Well, you'll notice the ratio of nitrogen to hydrogen is 1 to 3. So whatever nitrogen is, hydrogen will be 3 times as much. And whatever hydrogen is, nitrogen will be 1/3 of that. So since 1 mole of ammonia will decompose into 1 mole of nitrogen and 3 moles of hydrogen, 3 times as much hydrogen than nitrogen, the pressure of the hydrogen will be the pressure of the nitrogen times 3, since it's a 1 to 3 ratio. 3 times 6 would be 18 atmospheres. So you can apply this across the board. It's actually a very simple equation to use. So here's a problem involving vapor pressure. We have 100 milliliters of water and we put it into a 400 milliliter flask at 30 degrees Celsius and leave it to sit. So can you picture it? You've got a flask, it's got a little bit of water in it, it's about a quarter of the way filled with water. And and what this question doesn't say is that we seal it up. Okay, so we're going to put the water in the flask and we're going to seal it up. We're going to put a rubber stopper on the top of it at 30 degrees Celsius. And after a time, we notice condensation on the side of the flask. Now, if the air pressure in the flask was 100 kilopascals before it was sealed, what will the new total pressure be once you reach vapor-liquid equilibrium? Well, remember, the vapor pressure will add its pressure to the gas already in the flask. So if the pressure in the flask was 100 kilopascals, then the pressure after is going to be higher than 100. How much higher? Well, you got to go to reference table H and look it up. And when we go to reference table H, we'll notice that at 30 degrees Celsius, water's vapor pressure is only about 5 kilopascals. So our flask will contain 100 kilopascals worth of air and 5 kilopascals worth of water vapor. So we just simply add, and we add the two together. 4 or 5, either would be acceptable. So 104 or 105, depending on how you read the graph. All right. On to Graham's law of effusion, courtesy of Thomas Graham. You'll notice that the square root of molecular mass versus time to spread out, the lighter a gas is, the less time the gas requires to spread out from a central point. Heavier gases will require greater time to spread out. And this data allowed for the creation of Graham's law. Now, we're not going to do any math with this at this level. If you go on to college chemistry, then you'll actually do the math with if this is the molecular mass and this is the temperature, how long will it take for a gas to spread out to a certain distance? But we're not going to do that. All you need to know is that gases will spread out from a central point, like if a dog takes a poop on the corner of your lawn. Parts of it, the more higher vapor pressure components will evaporate, and those are typically the stinky components, and they will start moving out from the dog poop in a spherical manner. The rate of this spread is directly related to how hot it is, which means the hotter it is, the faster the spread will be, and inversely related to the molecular mass, which means the heavier it is, the slower it will be. So light, hot gases will spread out faster than cold, dense gases. So here's an application. Let's say we take hydrogen chloride and ammonia, and we put it in either end of a hollow tube, and the gases will meet somewhere in the tube. The hydrogen chloride will spread out, the ammonia will spread out, and we have to figure out where the two gases are going to meet. And we can do so because there will be a white solid of ammonium chloride that will form in the tube. Now, hydrogen chloride is made of hydrogen. Each atom of hydrogen has a mass of 1 gram per mole. Each mole of hydrogen, rather. Each mole of chlorine weighs 35.5 grams. So what's called the gram formula mass of hydrogen chloride is 36.5 grams for each mole. Ammonia has 1 nitrogen, 14.0, 3 hydrogens at 1.0 each, see the same amount, adds up to 17.0 grams per mole. That means ammonia is a little less than half as heavy as hydrogen chloride, which means it will be half as dense. So as a result, the ammonia should spread out faster than the hydrogen chloride. The ammonia will move really fast, the hydrogen chloride will move really slow, and the two of them should meet somewhere closer to hydrogen chloride and form this white solid. Well, let's see if that's what happens. Here we have the samples of the liquid soaked into cotton balls, and then you have the evaporation of the gases. You can see the ammonia coming from the left moving really fast, and the hydrogen chloride coming from the right moving really slow because it's heavier. And where they meet, you're going to form, and it'll show up as like little white molecules of ammonium chloride. So this is a demonstration that the lighter gas will travel much faster than the heavier gas. A gas at higher temperature will also move faster than a gas at lower temperature. So if we were to put this in a higher temperature situation, you'd see the molecules moving faster. The overall result would be the same. Ammonia is still lighter, hydrogen chloride is still heavier, which means ammonium chloride will travel faster than the hydrogen chloride. And that is as far as you have to take Graham's law of effusion as far as this course is concerned. The next time you meet, you'll be learning about gas laws. P1 V1 over T1 equals P2 V2 over T2. But until that happens, once again, I bid you adieu and bye.